Hi everyone. In this lecture, we will talk about the impact of the frequency response of an op-amp on the performance of op-amp based circuits. What do I mean by that is that so far we have discussed a wide range of op-amp based circuits to perform different mathematical operations. We discussed integrators, we discussed differentiators, summers, subtractors, we discussed amplifiers, inverting, non-inverting, and buffers. Now, all these amplifiers, while doing the analysis of all these circuits, we assumed op-amp to be a hypothetical three-terminal device with an infinite gain. But we already discussed that a practical op-amp has a finite DC gain. It has a finite bandwidth, meaning it has a frequency response wherein its gain is not infinite for all frequencies and it's going to decrease after a certain frequency. Okay, so which means it has a finite bandwidth. And then we discussed op-amp has a saturation limits. Its voltage cannot go to infinity, so there is a limit of what is the maximum and minimum values it can go to. Then we slowly started analyzing the impact of each of these op-amp non-idealities on the performance of these op-amp based circuits. In this lecture, we will exclusively focus on the impact of op-amp's frequency response characteristics on the closed loop op-amp based circuits. Okay, so just to quickly refresh your memory, we discussed the impact of DC gain. For example, op-amp having a finite gain. We said if you want to build an op-amp based circuit with a very large closed loop DC gain. So for example, for most op-amp based circuits, the DC, let's assume we are building an amplifier. The DC gain of the op-amp's amplifier will be very close to 1 by beta. Okay, let's say we need a gain of 10 power 3, then beta has to be equal to 10 power minus 3. So your feedback factor is really small. And we said that in one of the previous lectures that for you to realize a beta of 10 power minus 3 to realize a gain of 10 power 3, your A times beta, the open loop gain times the feedback factor, has to be much greater than 1. So therefore A has to be much greater than 1 by beta, or A has to be much greater than 10 power 3 or 1000. Okay, so and we said that generally as a rule of thumb, you choose at least 2 orders of magnitude higher so that you always meet this condition. A beta is much greater than 1. So that's how we arrived at this. We arrived at this condition when we were studying the impact of finite DC gain on the performance of op-amp based circuits. In this lecture, we will go a step further and we will consider the frequency response characteristics of an op-amp. Okay, so here we assume in the previous analysis when we included finite DC gain, for an op-amp, we assume that the DC gain is going to remain constant for all frequencies. But in practice, the DC gain will start decreasing after a certain frequency. Now, to mathematically model the impact of the decrease of DC gains with frequency, one of the most useful and standard models is to model the op-amp as a single pole response as shown here. Okay, DC gain and a single pole response. I mean, does the single pole response model work? And I'll argue that it works very well. How do you realize very high gain in op-amps? By cascading multiple stages. Now, when you cascade multiple stages, normally you end up introducing multiple poles. But what we do is that because when you introduce multiple poles, then we have a problem of stability. So generally we do frequency compensation. It's also called dominant pole compensation. And we convert the frequency response graph in such a way such that it looks like a first order response until around the UGB. Okay, around the unity gain frequency, it will more or less look like a first order transfer function. So this approximation is pretty good. It's a very good approximation for the frequency response model of an op-amp with a finite DC gain and a single pole at a low frequency. So if I plot this frequency response on a frequency scale, as a function of frequency, you can see that the gain will start rolling off after omega p. Omega p is the dominant pole in the op-amp. And then the frequency of interest to us is the unity gain frequency. That is the point at which this response, the frequency response, crosses the unity gain okay, where the gain becomes equal to 1. Or on a log scale, that's the point where your frequency response curve crosses the 0 decibel line. You can easily find it out when you're, I'm going to treat S as j omega. So for frequencies much greater than omega p, I can write the gain, the closed loop, the frequency response of the op-amp will become equal to omega p times A by S. No? I can ignore 1 here, you will get this term, A times omega p by S. So this product, DC gain times the first pole, the dominant pole, is what we call the UGB, or the unity gain bandwidth of the op-amp. This term, the UGB, we will later see as we analyze different amplifier architectures, plays a significant role. Okay, that's why if you read op-amp data sheets, many times they may not mention the pole frequency, but they will mention normally the DC gain and the UGB. These two are very important parameters. Okay, DC gain, because if you want to use your op-amp in a negative feedback mode, you have to keep in mind your beta cannot be very small. Okay, how small your beta can be, that is usually determined by the forward path gain, the DC gain of the op-amp. Then if you have to use it for a frequency dependent input, meaning if I have to use it for a time varying inputs. So for a DC inputs, for example, if I'm using this op-amp in some weight measurement system, for practical purposes, you can treat it like a DC input. There you will worry only about the DC gain of the op-amp. UGB may not really matter for all practical purposes. But if you are going to use this op-amp as a buffer for some high frequency amplifier, okay, or in some filter with some finite bandwidth, then UGB will matter. So in this lecture, we will study the impact of the frequency response characteristics of an op-amp on the performance of all these op-amp based circuits. Okay, we will see how, under what conditions does these op-amp based circuits behave as intended. Okay, so that's what we will discuss in this lecture. I'll also try to give intuitions what happens in time domain and also in frequency domain. So here the point to keep in mind is you have to know that UGB matters more and also DC gain. But in this lecture, as we will see, it is this term UGB which is of greater significance to us. Now before we start the analysis, I just want to quickly again brush your memory. If I have a negative feedback system that looks like this, the forward path gain is given by A of S. A of S is your op-amp's gain, given by A by 1 plus S by omega p. It's a single pole response, and put in a negative feedback. We already discussed this, which is why I'm just going to quote the final result. The closed loop gain, assuming A beta is much greater than 1, can be approximated to 1 by beta times 1 by 1 plus S by omega u. It will be omega p into 1 plus A beta. Okay, so if you guys can recall, what happens is that the DC gain becomes, it gets reduced by a factor of 1 plus A beta, and the pole increases by a factor of 1 plus A beta. So this I can approximate DC gain to be 1 by beta, and the pole can be, assuming A beta is much greater than 1, the pole is approximated to omega p times A beta. And omega p times A is called omega u, that's your UGB, times beta. So now if I put this amplifier with a op-amp with a finite frequency, with a finite UGB in negative feedback, the closed loop system also behaves like a single pole system with a DC gain of 1 by beta and a pole frequency of, or 3 dB bandwidth, which is equal to omega, this is called omega closed loop or omega 3 dB. This is the 3 dB closed loop bandwidth. Because it's a single pole system, I am using the word 3 dB bandwidth, is equal to beta times omega u. Okay, so the closed loop bandwidth depends upon two things, the feedback factor beta and the UGB of the op-amp. So you'll have to keep this in mind when we are analyzing the different op-amp based circuits. Now let's, okay, I'm just showing it on the frequency response curve. So which means this feedback system is supposed to give you ideally a DC gain of 1 by beta. If the op-amp's UGB is infinity, meaning if the op-amp's pole, first pole is at infinity, then it will remain constant. It will be 1 by beta for all frequencies. But if I take op-amp's finite UGB into account, then you can see that the closed loop response will have a 3 dB bandwidth, meaning after this frequency the gain will start decreasing with a single pole roll off, 20 decibels per decade roll off. And the closed loop bandwidth, the closed loop pole or the closed loop 3 dB bandwidth, so this will be omega 3 dB, will be beta times omega u. So that's how the frequency response curves looks like. Okay, so this negative feedback system will behave as intended, which means it is supposed to give you a gain of 1 by beta for this range of frequencies. The range of frequencies will be 0 to beta times omega u. If you apply your frequency within this range, you will get the desired gain of 1 by beta. Okay, any frequency greater than that, your gain will start decreasing. So in a few moments when we discuss buffers, I'll also see how does this translate to a time domain specification. So first we'll start with the simplest circuit, which is your buffer. The voltage buffer, a very commonly used circuit. I've discussed this. Whenever you want to drive resistive loads and your source impedance happens to be very poor, then we normally insert a buffer in between. So again, a buffer's DC gain is supposed to be 1. Beta in this case is just equal to 1. And a voltage buffer can be very easily modeled as this, the control loop model that we discussed in the previous slide. It can be mathematically modeled. Mathematically, it can be easily modeled by this control loop model. Okay, beta equals to 1, and you can easily model that in this way. Okay, so if you model that, if you keep that in mind, I can directly draw its frequency response graph. It's going to look something like this. 1 by beta is 0 decibels, beta is 1. It's going to remain constant for frequencies till UGB. Okay, beta is 1. So the pole, the 3 dB bandwidth of this closed loop amplifier is going to be omega u itself. Okay, guys, I'm not deriving this equation. I'm directly writing it because I just derived it for a general control loop, a general closed loop model. I'm using that same result here. You can arrive at the same result because it's a negatively fedback system with a finite open loop gain of A of s. Closed loop gain is given by A of s by 1 plus A of s. Using this result, you can also derive, you can easily show it will reduce to 1 by 1 plus s upon omega u. Okay, I can approximate it to this. It will behave like a single pole as a low pass filter with a DC gain of unity or 0 decibels and a 3 dB bandwidth equal to omega u. So what does this tell you? If you are going to use this op amp as a buffer, the maximum frequency that you can apply is limited by the UGB of the op amp. So if your UGB is 100 megahertz, then you can use this op amp as a buffer for frequencies in the order of tens of megahertz. I can't use this for a 1 gigahertz application, right? So that's what this means. I'm just explaining in very simple terms so that you get what this means. That's it. So now how do I interpret this in time domain? So I'll give an example. The example I'm going to talk about now holds true more for an integrated circuit op amp, but it's okay. I can give it as for example, I'm just giving it as an example to give you guys an idea of the significance of this UGB. Okay. So all these graphs tell you is that the buffer will act like a buffer till the UGB frequency. After that, it will no longer give you a gain of unity. It will start decreasing. That's what this graph is telling me. So how do I translate it to time domain? Can I think of one, of course, this directly makes sense that this puts a limit on the maximum frequency I can use this op amp circuit for. If I can use this buffer circuit for. Okay, it tells you your frequency cannot exceed the UGB of the op amp. The other way, you can also look at another interesting example. So let's say you have a sample and hold circuit, which you are then feeding it to an ADC, which will just directly convert an analog signal to, see, usually ADCs also contain sample and hold, but let's assume this is just a quantizer. This guy is just a quantizer. I'm calling it an ADC, but it is just a quantizer. It will convert, you feed an analog voltage, it will convert it to an equivalent digital value. Okay, so the input signal is sampled using a sampling clock whose time period is T. That's what I've shown here. Then you feed it through a buffer and the output of the buffer is fed to this quantizer. Okay, it goes to ADCs, comparators and all that. So why am I putting a buffer in between? Because the ADCs, comparators might have input capacitance, then you'll have to drive this capacitance. So to ensure that, if your source has a very poor source resistance, then you will not be able to charge the capacitor. If the capacitive load is very high, depending on what kind of input you are driving, the load can be very high. So usually whenever your load, I'm using the word high, the load is drawing a lot of current, then you put a buffer in between. Okay, so this is a very normal practice. The circuit may not exactly resemble this, but I have drawn an equivalent version to just show you guys how does UGB translate to a time how can I translate it, or what problem can it cause in a time domain. So this circuit, you're going to sample a sinusoidal some signal, and the goal is that once you sample it, the sampled signal should remain constant in a single cycle. So the output at this sampler's input, right, at the output of the sampler, it's going to look like a zero order whole waveform, meaning it's going to look like a step input. It will remain constant for one whole time period, and then suddenly it will increase to a different value, and so on, right? So its value is going to remain constant for that entire duration. That's what sample and hold is. You are going to sample it at this instant and hold that value for the entire time period. So it more or less will look like a step input, small step inputs at this comparator's input. The maximum step size can be equal to the peak to peak. If your sinusoidal signal is varying from a peak, if you apply for example, if you apply what you call as the Nyquist frequency, the samples of a sinusoid for a Nyquist frequency will be at one peak and other peak. So if you have a sinusoid of Nyquist frequency which is equal to Fs by 2, then you will normally take two samples. One sample will be at the peak, the other sample will be at the negative peak. This is how the sampling process will look like for a sinusoid at the Nyquist frequency. Okay, that's the frequency is Fs by 2 or 1 by 2t. So the peak to peak, the maximum delta, the maximum step change at this point will normally be equal to the peak to peak input of your the peak to peak value of your input signal, right? It's going to vary from negative peak to the positive peak. That's the maximum rate of maximum change in your input. So when you apply a step input, let's call it 0 to Vp, I'll call it Vpp, that's the V peak to peak. That's the maximum step input that can appear at the comparator's input. The output of the comparator, the output of the buffer, okay, this is a buffer, should also ideally be, if this Opamp's gain is UGB is infinity, then that will also just be a step whose value will go from 0 or some minimum value to a maximum value, and the difference between the minimum and maximum will be equal to V peak to peak. But we just said that the buffer, when you put it in negative feedback, assuming the Opamp having a finite UGB, the characteristic will look like this. It will look like a first order response. And we know for a first order response, if you feed a step input, the output is going to be an exponential charging, so asymptotic charging. So it's going to charge like this. Okay, so this is going to be V peak to peak times 1 minus e power minus t upon tau. Now this time constant for charging will be equal to 1 upon the bandwidth of this closed loop system, right? So we know the frequency response graph. From the frequency response graph, I can say what will be the time constant with which this system will respond. This is a closed loop system with a single pole. So if I apply a step input, you can already predict that it's going to respond with a first order time constant, a first order response with a time constant given by 1 by omega u, okay, for a single pole system. So it's going to increase with a time constant, it's going to increase with the time constant or rise with the time constant given by 1 by omega u. Okay, so ideally you would want this output to completely settle in one single time period. You don't want it to be rising and the output not settling in its cycle. So ideally you want it to fully settle down in a single cycle. And we said that, okay, one of the rules, right? What is the rule for condition for full settling is 5 time constants. So within a single period, your time period should be greater than 5 time constants. Time constant here is the time constant of the buffer. If this condition is met, then you can assume that the buffer is working fine. Your output has more or less settled and your ADC can do its conversion properly. Okay, it will immediately convert that analog voltage to a digital output. So within a time period T, your digital outputs will all stabilize to the right value. Okay, so this is the condition. So from this I can argue 5 time constants. I'll get your time period should be greater than 5 by omega u. From that I can derive a condition. If I know a sampling frequency for the ADC, Fs is 1 by T. Okay, then the UGB of the op-amp has to be greater than 5 Fs by 2 pi. So this is how I arrive at a condition. So if you are going to pick an op-amp for this application, this is a very I'm just trying to illustrate you the impact of UGB. So I've just picked an example. So if you have to pick if you have to design an op-amp, this is usually an integrated circuit problem. But let's say if you are building the circuit using discrete components, even then you'll have to keep this result in mind. So if you are going to build it for some sampling application and this buffer is used in that, then the UGB of this op-amp has to be greater than 5 Fs by 2 pi. Okay, this condition comes from a time domain specification, remember guys. So that's the important point I'm trying to make here, is that at time I was able to arrive at a condition for UGB starting from a time domain specification, that the output has to settle to its final value within a single sampling interval. From that I arrived at a condition what should be the UGB for that to happen. So that's one example of the impact of op-amp's finite UGB on the performance of a op-amp based circuit, here the circuit being a buffer. So the same rule applies for non-inverting amplifiers as well. In non-inverting amplifier, again a non-inverting amplifier can also be very easily modeled as a closed loop system with a control loop model in this manner, right? Forward path gain A and the feedback path can be written this way, and the closed loop gain for this is typically 1 by beta, where beta here is given by R1 by R1 by R2, R1 by R1 plus R2, that's the feedback quantity. So 1 by beta will be 1 plus R2 by R1, and this can be easily modeled as a control loop model with a forward path gain and a feedback factor of beta. Now if I take op-amp's frequency response into account, we said that the op-amp's closed loop response is going to look like this, right? The DC gain will be 1 by beta, and the 3 dB frequency, the maximum frequency until which this gain will more or less remain constant, is equal to omega u times beta, and that is given by omega u times R1 by R1 plus R2. So here, see guys, there is an important caveat here. So when you want to realize a very high gain, which means 1 by beta has to be very high, your bandwidth decreases. Okay, the bandwidth or the frequency until which you get that high gain also decreases. So if you want, let's say you want this non-inverting amplifier to act like an amplifier for a wide range of frequencies, let omega max be the frequency, then your UGB times beta has to be greater than omega max. Let omega max be the maximum input signal frequency. Then your UGB has to be greater than omega max upon beta. Okay, 1 by beta is A closed loop. So A closed loop times omega max, your op-amp's UGB has to be greater than this. Okay, if I tell you that this non-inverting amplifier should act like a non-inverting amplifier for a frequency of omega max, then the UGB of the op-amp has to be equal to or greater than A closed loop, which is 1 by beta times omega max. Okay, so that's where this frequency response plays a role. Okay, so if you have to pick an op-amp, you are going to pick an op-amp keeping this condition in mind. Okay, so this again tells you that if your beta is very small, if your beta is really small, the feedback factor is very small, then you need very high UGB as well. Okay, if you want to have it to operate over a wide range of frequencies, then you need high UGB as well. Not only DC gain, let's say if it's used, if this guy is used in a DC application, for example, a weight measurement system, then your DC gain has to be much greater than 1 by beta. That's it. This condition is satisfied. I'm fine with that. I don't have to worry about UGB, but if it's going to be used in a high frequency circuit or an application where the input signals are changing with time, then your UGB of the op-amp has to meet this condition. Okay, so this is something to keep in mind. And generally, if you are increasing the DC gain, your UGB will also be higher. Okay, but if you are decreasing, this is something to keep in mind, because UGB is what? It's the product of your pole times the DC gain of the op-amp. So if you are increasing A, UGB will also just increase. So I haven't in fact uploaded any video on my op-amp series lectures. So there we will discuss in great detail, probably whenever I get time, how do you set all these things, right? So when you increase UGB, when you increase DC gain, UGB will also decrease. There are several trade-offs there. So we'll talk about that. But right now this is a discrete op-amp case wherein you don't have much control on designing the op-amp. You are just a embedded designer who's going to pick an op-amp based on the specifications that you read from a data sheet. So I'm saying that from a data sheet, if you were to read, you just look for this. If you know the maximum frequency until which this circuit has to operate, and you know the feedback factor or the closed loop gain, then your UGB has to be greater than closed loop gain times the maximum input frequency. If you meet this condition, you're good. Okay. Now, finally, to the third amplifier architecture. I'm just taking some very common circuits that we have analyzed so far and showing you how their frequency response characteristics change. How the frequency response characteristics will look like if you assume op-amp has a finite UGB. Now, in case of a inverting amplifier, it is not as straightforward. I can't just directly draw a closed loop model like this. We said that, the closed loop gain is not equal to 1 by beta. It's not just 1 by beta for inverting amplifiers. For inverting amplifiers, it is slightly different. And I have already discussed the mathematical model for this. I request you to watch that video. I'm going to directly draw the final model here. This is the final mathematical model. You can reduce an inverting amplifier to this part. If you guys can recognize, this part is just a closed loop system, and then a closed loop op-amp in just feedback, right? That can be modeled as a closed loop control loop, a closed loop model, and there is an additional forward path gain, which is again dependent on the resistor R2 and all that. So this, I'm again quoting the final result. So if you look at this term, this is the term which is the feedback term, the feedback part of this block diagram is going to determine the frequency response. See, this doesn't have any frequency response dependence, only this term has. So therefore the feedback factor beta and the op-amp's open loop gain, that will determine the frequency response. So that's why I'm just showing this model to show you guys that the frequency response, the 3 dB bandwidth will remain the same as it was for a non-inverting amplifier. Okay, only that there is an additional DC factor that you have to multiply it with. That's the only difference between integrating and non-integrating, inverting and non-inverting amplifiers. So finally, I'll quote the final result. The DC gain is minus R2 by R1 multiplied by 1 by 1 plus S by omega U times beta. The 3 dB, it again acts like a first order system, but here the 3 dB bandwidth is omega U times beta. So that's what I've shown it in the frequency response curve. This is a magnitude response, so I have not put the sign here. So it's R2 by R1. So just for you guys to keep in mind, again, beta in the circuit is R1 by R1 plus R2. See, that's the feedback quantity. So if beta is very small, okay, which means R1 is much smaller than R2. Beta much smaller than 1, usually means R1 is much smaller than R2, then I can approximate this to R1 by R2. In that case, I can approximate this to 1 by beta. 1 by beta will simply be equal to R2 by R1. This is true only if your beta is really small, much smaller than 1. Then I can approximate, I can say that even an inverting amplifier's gain is close to 1 by beta. Okay, and the response is very close to, except for a negative sign, it's very close to that of a non-inverting amplifier. Okay, so again, even an inverting amplifier, the same rules apply. I mean, it's going to give you that gain of R2 by R1 within a bandwidth of omega u times beta. Okay, in this frequency range, you can get a gain of omega u times beta, and after that your gain will start rolling off. So that's what I'm trying to arrive at here. And the same conditions will hold true if I'm going to use it in time domain. Let's say I'm going to use this amplifier in time domain, okay, and then I apply a sudden step input. The output is going to raise with the time constant, where the time constant will be given by omega u times beta. Okay, so again, all the rules apply. If let's say I'm going to use this as a some front end circuit for some sampler or something like that, so then I'll have to meet those same conditions that we derived for a voltage buffer. Okay, so if I want the output to settle to 5 time constants within a single clock period, then naturally that translates to a higher UGB. Okay, your UGB has to be very high if you want your output to settle very quickly. Okay, so all that can be derived. So that's it about amplifiers, Opamp circuits, Opamp amplifier circuits, and how their frequency response characteristics change if I include Opamp's finite UGB. Okay, ideally these are just amplifiers, right? You would expect them to give you the desired gains for all frequencies. But if you consider Opamp's finite UGB, the characteristics change. Okay, then these circuits will have a finite, a different frequency response, and we studied how the frequency response graph will look like for the 3 popular architectures, which is voltage buffer, non-inverting amplifier, and inverting amplifier. Now I'll take a very interesting example, which is an voltage adder, and then see what impact will an Opamp's UGB, Opamp's finite bandwidth, have on the performance of an adder. How do you guys have to analyze the adder's performance taking Opamp's UGB into account? So here I'll explain the impact of Opamp's UGB on this adder's performance by taking a problem. It's a very interesting problem. I thought I'll just quickly discuss this. So consider an inverting adder with a finite DC gain. The DC gain is RF by R, which we are calling it as alpha in this example. And it has n inputs. It's a voltage adder with n inputs. And the gain of each path, for each input, the gain is RF by R. It's given as alpha. What is the UGB required from the Opamp? What is the Opamp's UGB that is needed if the maximum frequency of the signals, you have n different signals here, the maximum frequency it's given for all the signals is 1 megahertz. So omega max is given to be equal to 1 megahertz, and this is the maximum frequency of the inputs that you're applying to this adder. Assume n equals to 10, that is the number of inputs is 10, and alpha equals to 100, that is the gain for each path is 100. Now you are supposed to analyze this circuit. So first I'll just write the expression for the output, so you can apply superposition. And I said when you apply superposition, the other resistors will not matter, only the current will flow through this path for each voltage signal, and you can easily show that the output voltage will be minus of RF by R. This is the path gain times the sum of all these voltages. Okay, that's the expression, and in this case my RF by R is simply alpha, so I have written minus alpha times summed over all these voltages. Now to understand its frequency response, what I will do is I will find out what is the frequency response for each signal. Okay, for each signal I will find out what is the frequency response, and then I can apply again same rules of superposition hold true. So I can, if I want to find out VO of S, I can write it as, alpha 1 of S times minus alpha 1 times or I'll include the minus, alpha 1 of S times V1 of S plus alpha 2 of S times V2 of S and so on. Okay, I can include I'll include the minus sign in alpha S. So I can express my output in terms of this, and so therefore the rules of superposition can be applied here. So if I short all the inputs, you will have n minus 1 resistors coming in parallel, so that equivalent resistance will be R by n minus 1. And the resistance seen by V1 will be R. Now if you see this circuit, right, it's slightly different. The feedback factor is finite in the circuit, right? So always remember, anytime you are analyzing the inverting amplifier also, we discussed in the previous example that the closed loop UGB of the system is determined by the, I can just assume the input as short and analyze and find what is the analyze this circuit as it is. Okay, and treat whatever signal is fed back, and from that I can compute beta. Now if you see, all these n minus 1 resistors, right, they were all appearing in parallel. They will start loading the main resistor R. For each path, the resistor main signal current flows through the resistor R. The other resistors will carry feedback information. So that will come in parallel with your main resistor. So if I were to just short input and find the feedback path for this, feedback gain for this, this is the model, right? I've included even the resistor R in parallel with this. So this is the model where I'm drawing this model to find what is the feedback factor, right? The remaining, all I'm trying to say here is the remaining n minus 1 resistors will now load, and they will impact the quantity that is being fed back. So now if you see, the feedback factor in the circuit becomes 1 by 1 plus n RF by R. If there was no resistors if there were no resistors, the feedback factor would have been, see, this is R and R, and this is V1 or some VI. So I'm just saying VI is being any one of those ith input, where I being 1 to n, any one of those inputs. The feedback factor for this circuit is very simple. That would have been 1 by 1 plus RF by R. But now, because of these n resistors in parallel, the feedback factor decreases. Okay, the amount of quantity that is being fed back decreases. So your beta becomes smaller. So that's why I wanted to take an adder example to show you guys in an adder that the other resistors can decrease your feedback factor. Now, first step, let's say all the inputs are only DC inputs. I don't worry about, I'm just giving you this idea that the inputs are not changing. All the n inputs are DC inputs. Then if I pose you a question, what is the DC gain necessary for this circuit? Then you will have to use this condition. A beta has to be much greater than 1. This has to be satisfied. So your A beta has to be much greater than 1, or your A has to be much greater than 1 by beta will be 1 plus n RF by R, and which is 1 plus n times alpha. Alpha is RF by R. So this condition has to be satisfied. So in this example, it is given n is 10, alpha is 100. So A has to be much greater than 1000. So your gain has to be much greater than 60 decibels. As I said, a rule of thumb, take 2 orders of magnitude. So 2 orders of magnitude means 100 decibels. 2 orders of magnitude is 10 power 2. So plus 40 decibels. So 10 power 2 in 20 log of 10 power 2 is 40. So you add plus 40 to this, you get 100 decibels. So your DC gain has to be at least 100 decibels. Okay, that is if I were to ask you to find the DC gain. But we are interested in finding the bandwidth, the UGB of the Opamp, or what should be the constraints for the Opamp. That's what was asked in the question. DC gain, we didn't bother in this question. But if DC gain was asked, I'm just telling you how do you arrive at that condition. So if you're going to use this adder, you will not pick an Opamp whose DC gain is smaller than 600 decibels. So why am I saying this is because if ignore if you just consider the forward path gain, right? RF by R, alpha is given as 100, which is a large number. Alpha being 100 means 1 by beta is 100. I can treat this as, I gave an example that whenever you take this circuit, if RF by R is really large, I can approximate it close to 1 by beta for an inverting amplifier too. So which means your 1 by beta is 100. If I treat 1 by beta as 100, then from that calculation I can say 40 plus 40, 80 decibels is sufficient. 2 orders of magnitude greater than 100, that should be sufficient. But you will be making a mistake because you are not including the loading effect of other resistors. When you consider all that, in this example, it turns out you have to be at least 100 decibels. Okay, that extra 20 decibels comes from the loading effect, the factor n. If the factor n is 1, then it's 40 dB, the gain was supposed to be just 100, which is 40 decibels. Gain has to be much greater than 100. So 100 is 40 decibels plus 40 for margin, you will get 80 decibels is the open loop gain needed. But you will be making a mistake because you are not including the loading effect of the other resistors. So that's for DC gain. Now for UGB, again we'll have to do the same calculation. So as I said, this is just if you look at this circuit, it's just an inverting amplifier. And all those same conditions will hold true. The Opamp's DC gain is going to be RF by R for each path. So this is the frequency response. There are n different paths. For each path, the frequency response DC gain is going to be close to RF by R. Okay, but the frequency response here is going to be the bandwidth, 3 dB bandwidth is going to be beta times omega u. So that is going to be 1 by 1 plus n alpha. Since n alpha is 1000, which is much greater than 1, I can approximate beta to be equal to 10 power minus 3. So your UGB, beta times omega u is your UGB. This has to be greater than omega max. Your maximum input frequency is given as 1 megahertz. So your omega u has to be greater than omega max upon beta, which will be omega max in this case is 1 megahertz. 1 by beta is 10 power 3. So it will be 1 gigahertz. You need your UGB to be at least 1 gigahertz for this Opamp, so that this adder circuit will behave like an adder for a frequency range of 1 megahertz. So that's how you calculate, and that's how if you are to pick an Opamp, you have to keep this in mind. If your input frequency range is given, then you have to choose an Opamp with an UGB of at least 1 gigahertz for the circuit to work properly. So that's it about amplifier frequency response. The next lecture, I'll start talking about frequency dependent Opamp based circuits like integrators, differentiators, and other practical integrators and differentiators, and how do these characteristics change with Opamps once you take Opamp's UGB into account. Thank you.